Welcome back. Today, our goal is to solve the side-side-side case of a triangle. Now, let's imagine we have an acute triangle. And in this triangle, we have been given all three of the side lengths, but we have no angles. And our experience with the law of sines suggests that it's really hard to use that one when we don't have any angles. So, let's drop the altitude, call it h. And what we're going to do, that's a little bit different this time, is we're going to declare a new variable. From here to here is going to be called x, which means the remainder here is c, take away x. And we look at the right triangle over here and say the Pythagorean theorem says c minus x squared plus h squared is equal to a squared. Right? This is leg, and a hypotenuse, so the Pythagorean theorem works just like that. Now, what we're going to then do is take this angle A and say the definition of sine says sine of angle A is opposite over hypotenuse, which then allows us to multiply the b over and say h is equal to b times sine of A. And then we say the definition of cosine allows us to say adjacent over hypotenuse, and then solve for x as x is equal to b times cosine of A. Then we're going to take these two and substitute them into there, which says c minus b cosine of A squared plus b sine of A squared is equal to lowercase a squared. All right, everything's good. Then it's time for algebra. I'm going to take this and expand c squared minus 2 times c times b times cosine of A plus b squared times cosine squared of A. All of this comes from that expansion. Then I'll take this squared, and I'll get b squared sine squared of A. At this stage, we realize that there's a b squared here and here, which allows us to factor out a b squared and perhaps simplify. And hopefully remember from last chapter that cosine squared plus sine squared is equal to 1. So all of this turns into 1, which then allows us to write c squared minus 2cb cosine A plus b squared times 1 is equal to a squared. And generally the way we write this is we'll put the a squared on the left, and it'll look like this. I'll put the b first because of alphabetical order. I'll put the c next, and then go 2, b first, then c, because alphabetical order, times cosine of A. And this is a very nice equation that relates the three side lengths and then an angle that we were not given. Now let's imagine we have an obtuse triangle. So let's have angle A be the obtuse angle. And then we're given all three of the sides, but none of the angles. We'll drop the altitude, call that length h, and we'll call this length x. And we're going to write the Pythagorean theorem for this large right triangle, which means that this entire side is c plus x from there to there. So we can write c plus x squared plus h squared is equal to a squared. So we see this is leg, and then the hypotenuse. Okay. Just like we did before, but this time we're going to look at that angle, which, since this is A, the angle that is represented by the dot is pi minus A. That would be the supplement. And we're going to write down sine of pi minus A is equal to opposite over hypotenuse. Now, hopefully you remember the identity that sine of pi minus A is the same thing as sine of just A. And I can multiply the b over, so I get h is equal to b times sine of angle A. All right. For the cosine, cosine of pi minus A is equal to adjacent over hypotenuse, which is x over b. And here we're going to use the angle difference identity that says cosine of pi times cosine of A plus sine of pi times sine of A. Then we remember that cosine of pi is -1 and sine of pi is 0. So this becomes -1 times cosine A is equal to x over b. And we'll multiply the b across and say x is equal to -b times cosine of A. Now, you might object and say, but x is a length. X cannot be negative. It actually is not negative, because cosine of A, think, A is an obtuse triangle in the standard position that's in the second quadrant, which means cosine of A is negative. So negative of a negative number is positive, and all is right in the universe. So it's time to substitute. We substitute this, and we realize we're writing the exact same relation that we had before. At the risk of boring you, I'm going to quickly write out the results. And we're going to factor the b squared out. And remember that all of this becomes 1 by the Pythagorean theorem. In which case, we can write a squared is equal to, in alphabetical order, b squared plus c squared minus 2bc times cosine of A. And we realize we have the exact same relation we did before, of course, because we started with the same relation we had before. This means that this equation holds true for obtuse triangles with obtuse angle A and acute triangles with acute angle A. We just have to show that this works for the right triangle case, and like we did before, we can say this is a formula that works for any angle. Let's consider the final case with a right triangle. Now, all we need to show is that a squared is equal to b squared plus c squared minus 2bc times cosine of A. And if this is true for the right triangle, then we now know it's true for any possible angle A. Well, cosine of a right angle, cosine of pi over 2 is equal to 0, which means this entire term drops out, and we have a squared is equal to b squared plus c squared, which is true by the Pythagorean theorem. So that means we can write down a squared is equal to b squared plus c squared minus 2bc times cosine of A, and argue that this is true for any angle A. This is the law of cosines. Now we can do even better, because if we look at this and we look at the organization of information, the angle A and its opposite side, those two are the sides surrounding A. So if this is true for any angle A, it has to be true for any angle B or any angle C. So let's look from B's perspective. From B's perspective, we'll populate the opposite side to B, and then the two sides surrounding B are going to be A and C. And then from angle C's perspective, the opposite side, C, and then the two surrounding sides, A and B, those three variations of the law of cosines are true for any angles in any triangle. And that is how we're going to deal with the side-side-side triangle. Now let's do an example. Let's say you're given side A, side B, and side C for a wonderful side-side-side case. And your goal is to solve the triangle. We want angles, so we can use any one of these. We might as well start with the top one and see where it takes us. And we're looking for the angle, so we'll isolate cosine of A. We'll subtract b squared and c squared over here. And then we'll divide by negative 2bc. And here we have it. We've successfully isolated cosine of A. So if we put in the values we were given, 20 squared minus 8 squared minus 14 squared all over negative 2 times 8 times 14. And this is equal to cosine of A, which we can compute to be this number, negative 0.625. We remember that cosine represents the x-coordinate in the unit circle. So we're looking for angles where the x-coordinate is negative 0.625. And we realize there are two places in the unit circle where that occurs. Is this an ambiguous case? Well, no, because this angle in the third quadrant is bigger than 180 degrees, which means it cannot occur in a triangle. In fact, if this number is negative, you get one solution in the second quadrant, so we're an obtuse angle, one solution in the third quadrant, which can't happen. If you have a positive number here, you get one solution in the first quadrant for an acute angle, and one solution in the fourth quadrant, which can't happen in a triangle. So, there's only one solution we need to worry about, which is cosine inverse of negative 0.625, which incidentally is approximately 128.7 degrees. And there we have an angle A. So we can begin to draw the triangle. Angle A, 128.7 degrees. And we know if we put angle B here, that this side, B equals 8, and then this side, C equals 14, and then we can close the triangle out with lowercase a is equal to 20. Now let's continue by finding angle B. We could use the law of sines since we have an angle and opposite side combination now, but since we're talking about the law of cosines, let's just use the law of cosines to find angle B. I want to isolate cosine B. I'll subtract over a squared and c squared, and then divide by negative 2ac. Then I'll substitute the numbers I have. So I'll have B is 8, A is 20, and C is 14. When we do this, the calculator tells us that that number comes out to 0.95. And then we remember that there's only one solution that we care about, and that is the cosine inverse of that number, which comes out to be 18.2 degrees. So now we have that B is equal to 18.2 degrees. And now that we have two angles, we can find C by saying that the three angles in a triangle must add up to 180 degrees, which leaves that C must be 180 degrees. Take away A, and take away B. And we can put approximately equal here because we're dealing with rounded quantities now. So C is approximately equal to 33.1 degrees, and there we have it, a fully solved side-by-side case of a triangle. Let's do another example. Let's say we have angle A, we have side B, and side C, and we want to solve the triangle. If we have an angle, it makes it much easier to draw. Let's put angle A in the lower left, and we'll put angle B in the lower right, which means side B is going to be 10. And opposite of angle C, side C is going to be 16. And then I'll close out the triangle with A over here. We have side, angle, side. So this case is different from before. I have angle A, and I have sides B and C, so I'm going to use the top one with the law of cosines to find the side length A. If I substitute, well, I don't know A, so I'll leave that as the variable. Lowercase b is 10. Lowercase c is 16. minus 2 times lowercase b times lowercase c times the cosine, and angle A is 71 degrees. So if we plug all those numbers into a calculator, we get that A squared is approximately 251.8. And then we take the square root, and we only worry about the positive root because A needs to be a positive number. So A is approximately equal to 15.87. We have our last side. Now we have all three sides and we want to find angle B. We could use the law of sines with this side and angle pair, or we could use the law of cosines. And since we're talking about the law of cosines today, let's do that. So let's go. B squared is equal to A squared plus C squared minus 2AC times cosine of B. And we're going to isolate for cosine of B. So we'll subtract these over, and we'll divide by negative 2AC. Then we can substitute. B is 10. We already found A. And it's important to try not to round at this stage so you get a better answer at the end. And C is 16 divided by negative 2 times A times 16. And I'm going to go ahead and write this as approximately equal to because I'm writing the rounded values here. So it turns out when I do this, I get that cosine of B is approximately equal to 0.8031. And then there's only one solution that can happen in this triangle, and that's going to be that B is approximately the cosine inverse of 0.8031, which gets us B is approximately equal to 36.6 degrees. Now that we have 2 out of the 3 angles, we can say the 3 angles must add up to 180 degrees. And we can find the last angle C by subtracting these 2 away from 180. And finally, we say that C is approximately 72.4 degrees. And there is our final angle, and we have solved the triangle. So to summarize our discussion on solving triangles, we've encountered these cases with the given information. So far, our experience tells us that when we have 2 angles given, in these 2 cases, the easiest way to begin the problem is to use the law of sines. And this was in the video for 6.1.1. And then we said, in the case where you have an angle, a side, and then another adjacent side, this could yield the ambiguous case when we approach it with the law of sines. And this was in the video 6.1.2. And then today, we discovered that these 2 cases, easiest to approach using the law of cosines. And there we have it. These are all the types of given information that we can use to solve triangles. Thanks for watching. Take care.